Section 19 of Scientific American Supplement Number 415, December 15, 1883. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Scientific American Supplement Number 415, December 15, 1883, by Various. Recent Studies on the Constitution of the Alkaloids, by Samuel P. Sattler, Ph.D. Introductory Lecture, Course of 1883 through 84, Philadelphia College of Pharmacy. The sciences of today present, as might be expected, a very different aspect from the same branches of knowledge as they appeared 50 or 60 years ago. It is not merely that the mass of observations in most of these lines of study has enormously increased during this interval. Were that all, the change could hardly be considered as an unmixed benefit, because of the increased difficulty of assimilation of this additional matter. Many would be the contradictions in the observations, and hopeless would be the task of bringing order out of such a chaos. The advance in the several branches of knowledge has been largely one resulting from improved methods of study rather than one following simply from diligence in the application of the old ways. Let us turn to chemistry for our illustration of this. The chemistry of the last century and the early decades of this was largely a descriptive science, such as the natural history branches, zoology and botany, are still in great part. Reasonably exact mineral analyses were made, it is true, but the laws of chemical combination and the fundamental conceptions of atoms and molecules had not been as yet generally established. Now this want of comprehensive views of chemical reactions, their why and wherefore, was bad enough as it affected the study of inorganic and metallic compounds, but what must have been the conditions for studying the complex compounds of carbon, so widely spread in the vegetable and animal kingdoms? Their number is so enormous that, in the absence of any established relationships, not much more than a mere enumeration was possible for the student of this branch of chemistry. It is only within the last 20 years that chemists have attained to any comprehensive views at all in the domain of organic chemistry. It has been found possible to gradually range most carbon compounds under two categories, either as marsh gas or as benzol derivatives, as fatty compounds or as aromatic compounds. To do this, methods of analysis very different from those used in mineral chemistry had to be applied. The mere finding out of percentage composition tells us little or nothing about an organic compound. What the elements are that compose the compound is not to be found out. That can be told beforehand with almost absolute certainty. What is wanted is to know how the atoms of carbon, hydrogen, oxygen, and nitrogen are linked together. For, strange to say, these differences of groupings which may be found to exist between these 3 or 4 elements endow the compounds with radically different properties and serve us as a basis of classification. The development of this part of chemistry, therefore, required very different methods of research. Instead of at once destroying a compound in order to learn of what elements it was composed, we submit it to a course of treatment with reagents which take it apart very gradually or modify it in the production of some related substance. In this way we are enabled to establish its relations with well-defined classes and to put it in its proper place. Of equal importance with the analytical method of study, however, is the synthetical. This method of research, as applied to organic compounds, embodies in it the highest triumphs of modern chemistry. It has been most fruitful of results, both theoretical and practical. Within recent years, hundreds of the products of vegetable and animal life have been built up from simpler compounds. Thousands of valuable dye colors and other compounds used in the arts attest to its practical value. It may therefore seem anomalous when I say that one of the most important of all the classes of organic compounds has not shared in this advance. The alkaloids, that most important class, from a medical and pharmaceutical point of view, have until quite recently been defined in the books simply as, quote, vegetable bases containing nitrogen, unquote. Whether they were marsh gas or benzol derivatives was not made out. How the 4 elements, carbon, hydrogen, oxygen, and nitrogen, were grouped together in them was absolutely a thing unknown. Chemists all admitted 2 things. first, that their constitution was very complex, and second, that the synthesis of any of the more important medicinal alkaloids would be an eminently desirable thing to effect from every point of view. Within the last 5 years, however, quite considerable progress has been made in arriving at a clearer understanding of these most important compounds, and I shall offer to your attention this evening a brief statement of what has been done and what seems likely to be accomplished in the near future. It was early recognized that the alkaloids were complex amines or ammonia derivatives. The more or less strongly marked basic character of these bodies, the presence of nitrogen as an essential element, and above all, the analogy shown to ammonia in the way these bases united with acids to form salts, not by replacement of the hydrogen of the acid, but by the direct addition of acid and base, pointed unmistakably to this constitution. But with this granted, the simplest alkaloid formulas, those of conine, C8H17N, and nicotine, C10H14N2, still showed that the amine molecule contained quite complex groups of carbon and hydrogen atoms, and the great majority of the alkaloids, the non-volatile ones, contain groups in which the three elements, carbon, hydrogen, and oxygen, all entered. Hence the difficulty in acquiring a knowledge of the molecular structure of those alkaloids at all comparable with that attained in the case of other organic compounds. Of course, synthesis could not be applied until analysis had revealed something of the molecular grouping of these compounds, so the action of different classes of reagents was tried upon the alkaloids. Before summarizing the results of this study of the decomposition and alteration products of the alkaloids, a brief reference to a related class of organic compounds will be of assistance to those unfamiliar with recent researches in this field. It is well known that in coal tar is found a series of ammonia-like bases, aniline or amidobenzol, toluidine or amidotoluol, and xylidine or amidoxylol, which are utilized practically in the manufacture of the so-called aniline dicolors. It is perhaps not so well known that there are other series of bases found there too. The first of these is the pyridine series, including pyridine, C5H5N, picoline, methylpyridine, C5H4N, CH3, lutidine, dimethylpyridine, C5H5N, CH3, and collidine, trimethylpyridine, C5H2N, CH3. This series is also found in relatively larger proportion in what is known as Dippel's oil, the product of the dry distillation of bones. The second series is the quinoline series, including quinoline, C9H7N, lepidine, methylquinoline, C10H9N, and cryptidine, dimethylquinoline, C11H11N. The two compounds which give name to these series, pyridine, C5H5N, and quinoline, C9H7N, respectively, bear to each other a relation analogous to that existing between benzol, C6H6, and naphthalene, C10H8. And the theory generally accepted by those chemists who have been occupying themselves with these bases and their derivatives is that pyridine is simply benzol in which an atom of nitrogen replaces the triad group CH, and quinoline, the naphthalene molecule, with a similar change. Indeed, Ladenburg has recently succeeded in obtaining benzol as an alteration product from pyridine in certain reactions. Moreover, from methylpyridine, C5H4N, CH3, would be derived an acid known as pyridine carboxylic acid, C5H4N, COOH, just as benzoic acid, C6H5, COOH, is derived from methylbenzol, C6H5CH3, and from dimethylpyridine, C5H3N, CH3, an acid known as pyridine dicarboxylic acid, C5H3N, COOH2, just as phthalic acid, C6H4, COOH2, is derived from dimethylbenzol, C6H4, CH3, The same thing applies to quinoline as compared to naphthalene. We may now look at the question of the decomposing effect of reagents upon the alkaloids. The means which have proved most efficacious in decomposing these bases are the action of oxidizing and reducing agents, of bromine, of organic iodides, of concentrated acids and alkalis, and of heat. Taking up the volatile alkaloids, we find with regard to conine, first, that the action of methyl iodide shows it to be a secondary amine. That is, it restrains only one replaceable hydrogen atom of the original ammonia molecule. Its formula is therefore C8H16NH. From conine can be prepared methylconine, which also occurs in nature, and dimethylconine. From this latter has been gotten a hydrocarbon C8H14 conylene homologous with acetylene C2H2. Conine, on oxidation, yields chiefly butyric acid, but among the products of oxidation has been found the pyridine carboxylic acid before referred to. The formula of conine, C8H17N, shows it to be homologous with piperidine, C5H11N, a derivative of piperine, the alkaloid of pepper, to be spoken of later, and just as piperidine is derived from pyridine by the action of reducing agents, so conine is probably derived from a propylpyridine. The artificial alkaloid paraconine, isomeric with the natural conine, will be referred to later. Nicotine, C10H14N2, the next simplest in formula of the alkaloids, is a tertiary base. That is, contains no replaceable hydrogen atoms in its molecule. It shows very close relations to pyridine. When nicotine vapor is passed through a red-hot tube, it yields essentially collidine, and with this some pyridine, picoline, lutidine, and gases such as hydrogen, marsh gas, and ethylene. Heated with bromine water to 120 degrees centigrade, it decomposes into bromoform, carbon dioxide, nitrogen, and pyridine. When its alcoholic solution is treated with ferrocyanide of potassium, it is oxidized to dipyridine, C10H10N2. Potassium permanganate, chromic or nitric acid, oxidizes it to nicotinic acid, C6H5NO2, which is simply pyridine carboxylic acid, C5H4N, COOH, and which, distilled over quicklime, yields pyridine, C5H5N. Turning now to the non-volatile and oxygenized bases, we take up first the opium alkaloids. Morphine, C17H19NO3, is a tertiary amine, and appears to contain a hydroxyl group like phenols, to which class of bodies it has some analogies, as is shown in its reaction with ferrochloride. Its methyl ester, which can be formed from it, is codeine, one of the accompanying alkaloids of opium. Besides the methyl derivative, however, others are possible, and several have been recently prepared, giving rise to a class of artificial alkaloids known as codeines. Morphine, rapidly distilled over zinc dust, yields phenanthrene, trimethylamine, pyrrole, pyridine, quinoline, and other bases. The action of strong hydrochloric acid upon morphine changes it into apomorphine, C17H17NO2, by the withdrawal of a molecule of water. Ferrocyanide of potassium and caustic soda solution change morphine into oxydimorphine, C34H36N2O6. When heated with strong potassium hydrate, it yields methylamine. Narcotine, another of the opium alkaloids, when heated with magnesium dioxide and sulfuric acid, is oxidized and splits apart into opianic acid, C10H10O5, and cotarnine, C12H13NO3. This latter, by careful oxidation, yields apophyllenic acid, C8H7NO4, and this, on heating with hydrochloric acid to 240 degrees centigrade, yields pyridine dicarboxylic acid, C5H9N-COOH2. The base cotarnine also results from the prolonged heating of narcotine with water alone. In this case, instead of opianic acid, its reduction product, meconine, C10H10O4, is produced. Meconic acid, C7H4O7, which is found in opium in combination with the different bases, has also been investigated. By acting upon meconic acid with ammonia, cominamic acid is formed, and this latter, when heated with zinc dust, yields pyridine. If we go now to the cinchona alkaloids, we meet with exceedingly interesting results. Quinine, C20H24N2O2, when carefully oxidized with chromic acid or potassium permanganate, yields a series of products. First is formed quinidine, C19H22N2O4, a weak base, then quininic acid, C11H9NO3. Then the so-called oxycinchomoronic acid, C8H5NO6, cinchomoronic acid, C7H6NO4. Now the two acids last mentioned are simple substitution products of pyridine. Oxycinchomoronic acid being a pyridine dicarboxylic acid, C5H2N, COOH3, and cinchomoronic acid, a pyridine dicarboxylic acid, C5H3N, COOH2. When distilled with potassium hydrate, quinine yields quinoline and its homologs. The alkaloid has been shown to be a tertiary base. Quinidine yields with chromic acid the same decomposition products as quinine. Cinchonine, C19H22N2O, the second most important alkaloid of these barks, when oxidized with potassium permanganate, yields cinchonic acid, which is a quinoline carboxylic acid, C9H6N, COOH. Cinchomoronic acid, which has just been stated to be a pyridine dicarboxylic acid, and a pyridine tricarboxylic acid. When cinchonine is treated with potassium hydrate, it is decomposed into quinoline and a solid body, which on further treatment yields a liquid base, C7H9N, which is probably lutidine. It has been found, moreover, that both tetrahydroquinoline and dihydroquinoline, hydrogen addition products of quinoline, are present. When cinchonine is distilled with solid potassium hydrate, it yields perol and bases of both the pyridine and quinoline series. Cinchonidine, when heated with potassium hydrate, yields quinoline also, and with nitric acid, the same products as cinchonine. Strychnine has been found to be a tertiary amine. When distilled with potassium hydrate, quinoline is formed. Brucine is a tertiary diamine, that is, formed by substitution in a double ammonia molecule. When distilled with potassium hydrate, it yields quinoline, lutidine, and two isomeric collidines. The alkaloid atropine has been quite thoroughly studied with results of great interest. When heated with baryta water or hydrochloric acid, it takes up a molecule of water and is split into tropine, C8H15NO, and tropic acid, C9H10O3. This latter is phenyloxypropionic acid. Tropine, when heated to 180 degrees with concentrated hydrochloric acid, splits off a molecule of water and yields tropidine, C8H13N, a liquid base with an odor resembling conine. When this tropidine is heated with an excess of bromine, it yields dibromopyridine. Piperine, the alkaloid of pepper, has also been well studied. When boiled with alcoholic potash solution, it takes up a molecule of water and splits apart into pipperic acid, C12H10O4, and piperidine, C5H11N. This latter base has been shown to be a hydrogen addition product of pyridine, C5H5N. When heated with concentrated sulfuric acid, it is oxidized to pyridine. Piperidine hydrochlorate also, when heated with excess of bromine to 180 degrees centigrade, yields dibromopyridine. Sinapine, the alkaloid which exists as sulfocyanate in white mustard seed, yields, under the same reaction as that applied to atropine and piperine, quite different results. When boiled with baryta water, sinapine decomposes into sinapic acid, C11H12O5, and choline, C5H15NO2, the latter a well-known constituent of the bile, and produced also in the decomposition of the lecithin of the brain and yolk of egg. Cocaine, the alkaloid of coca leaves, is decomposed by heating with hydrochloric acid into methyl alcohol, benzoic acid, and a crystalline base, econine, C9H15NO3. Caffeine and theobromine have also quite different relations. Caffeine, it will be remembered, is the methyl ester of theobromine and can be prepared from it, when caffeine is carefully oxidized with chlorine, it yields dimethylalloxan and methylurea. Both theobromine and caffeine are decomposed by heating to 240 degrees centigrade in sealed tubes with hydrochloric acid, identical products being obtained. These products are carbon dioxide, formic acid, ammonia, methylamine, and sarcosine, the last three being, of course, in combination with the excess of hydrochloric acid. The artificial preparation of theobromine and caffeine from xanthine and guanine also show clearly their relations. If, having completed our survey of what has been done in the way of decomposing the alkaloids by the different classes of reagents, we review the field, it will be seen that with all the alkaloids mentioned, except the last four, a more or less immediate connection with the pyridine and quinoline bases has been indicated. The conviction accordingly forces itself upon us that, if we want to attack the problem of building up any of these important alkaloids artificially, we must turn to these bases as our starting point. As already stated, both series occur in coal tar, and the pyridine series also more abundantly in bone oil. Pyridine, picoline, lutein, and collidine, the first four members of the pyridine series, have moreover all been formed synthetically, although the processes are not such as would yield the products as cheaply as they can be gotten from Dippel's oil. Quinoline, the first member of the higher series, had been made synthetically by several chemists, but by expensive and involved methods, when Scropp, in 1881, effected its synthesis from nitrobenzol and glycerin, or still better, a mixture of nitrobenzol and aniline with glycerin. This process allows of its being made on a commercial scale if desirable. Shortly after, by an application of the same principle, Dobner and Miller effected the synthesis of lepidine, the second member of the quinoline series. At the same time that this general agreement to consider these bases as the starting point in the endeavor to effect the synthesis of the natural alkaloids had been arrived at by chemists, it was thought well to look into the question whether these bases and their immediate derivatives had any therapeutic value of their own. Piperidine, the decomposition product of piperine, which we have shown may be considered to be hexahydropyridine, was examined by Dr. Kronecker of Berlin at the request of Professor Hoffmann, and was found to have an action upon animals in many respects resembling that of conine. Professor Filena of Erlangen, who has studied a large number of these pyridine and quinoline derivatives, found, moreover, that the hydrochlorate of ethylpiperidine had a physiological action quite analogous to that of conine. The physiological action of quinoline itself has been studied quite extensively by Donath and others, and it was found that several of its salts were quite valuable febrifuges, acting very like quinine, and capable in cases of being used as a substitute for it. In general, the hydrogen addition products were found to be more active than the simple base, an observation entirely in accord with the theory formed by Vishnegradsky and by Koenigs as the result of the study of the decomposition products of the alkaloids, namely, the alkaloids are in general hydrogen addition products of pyridine and quinoline, or of the two bases combined. Thus, Professor Filena found that the hydrochlorate of tetrahydroquinoline was much more energetic in its action than quinoline, but could not be used on account of a too powerful local effect. The hydrochlorate of dimethyl tetrahydroquinoline, which was distinguished by its strong bitter taste, much resembling that of quinine, had an effect like that of curare poison. The most decided febrifuge action, however, was found by Professor Filena to reside in the hydrochlorate of oxyhydromethylquinoline, introduced to public notice by Professor O. Fischer under the name of Carin, and in the acid sulfate of tetrahydromethylquinoline, introduced under the name of Caroline. These compounds had a very surprising febrifuge action without any unpleasant after-effects or local disturbances. The most active workers in the field of synthetic formation of the alkaloids have been Vishnegradsky of St. Petersburg, who, unfortunately for science, died at an untimely age in 1880, Koenigs and Fischer of Munich, and Ladenburg of Kiel. The study of the decomposition products of the cinchona alkaloids especially points quite distinctly to the probable existence in quinine of a hydrogen addition product of pyridine, in combination with a methylquinoline group. The many experiments that are now being made to test this and other questions that suggest themselves will not long leave us in the dark. Whether a practical commercial synthesis of quinine will follow is another matter, but it is within the bounds of possibility, or perhaps even of probability. It must not be supposed that no syntheses of alkaloids have been effected as yet. By heating butylaldehyde with alcoholic ammonia is formed paraconine, an alkaloid isomeric with the natural conine, but differing in physiological action. By the action of sodium upon pyridine is produced a compound C10H8N2 known as dipyridal, and this, under the influence of nascent hydrogen, takes up 6 atoms and becomes isonicotine, C10H14N2, a physiologically active alkaloid isomeric with the true nicotine. The formation of a series of alkaloids under the name of codeines, by the substitution of other organic radicals instead of methyl in the codeine reaction, has already been alluded to. Atropine can be formed by uniting tropine and tropic acid, the 2 decomposition products already noted. The latter of these products is already shown to be capable of synthetical formation, and the other will no doubt be formed in the same way. The artificial atropine is identical with the natural alkaloid. Ladenburg has also formed a series of artificial alkaloids, called tropines, by uniting the base tropine with different organic acids, as in the case of the compound of mandelic acid and tropine, known as home atropine, an alkaloid of action similar to atropine, but possessing some decided advantages in its use. Piperine has also been made by the uniting of piperidine and piperic acid, and as piperidine has already been formed from pyridine, we have here a true synthesis also. Both theobromine and caffeine, its methyl derivative, have been made from xanthine, which itself can be formed from guanine, a constituent of guano. We may conclude from this reference to what has been done in the last few years that the reproach mentioned in first speaking of the alkaloids as a class, that almost nothing was known of their constitution, will not long remain, and that as their molecular structure is laid bare in these studies now being made, keen-sighted chemists will effect their artificial formation. When these most valuable compounds can be made by exact methods, in a state of entire purity, and at a cost much below that paid for the present extraction of them from relatively rare plants, organic chemistry will have placed all of us under obligations as great as those owing any branch of science, no matter how practical we call it. American Journal of Pharmacy. End of section 19.